Hello, my name is Kevin Stala. I will be presenting about the effect of laser remelting in titanium alloys as titanium 6 aluminum for vanadium. The presentation is based on an article that presented findings of using selective laser melting with this titanium alloy. It is known that this alloy is commonly used in industry as it possesses high specific strength, desirable tribological properties, which deals with the design, friction, wear, and lubrication properties, and it has excellent corrosion resistance, which helps to prevent environmental deterioration. Also, selective laser melting offers flexible layer-by-layer control strategy, and it uses titanium alloys powders and uses a novel melting strategy to avail further benefits of this technology. The combination of both attracts attention in the manufacturing of titanium-based alloys. The lack of information in this topic led the authors to contribute with effects of remelting on the microstructure and mechanical properties methodically. For the experiments, gas atomized powder was used. The right top corner picture shows that these powder particles have a spherical shape, although there are several satellites attached to the powder particles. The laser melting sequence can be observed on the left bottom picture, where the single melting is when the laser scans the powder very selectively once, so after the melt pool solidifies, the next layer of powder is deposited and the process iterates until it is done. For the double melting is when the laser scans the powder very selectively to melt the powder, and after it solidifies, the surface is scanned again by the laser with the same process parameters, but this time it's hatch style rotated to remelt the solidified part. So once it is solidified, the second layer of powder is deposited and the process iterates until done. For the triple melting, it follows the same process as double melting, but before adding the second layer of powder, the solidified part is scanned again a third time with a hatch-style rotation to remelt it. After solidification, the next layer of powder is added and the process iterates until it is done. These three processes were used to create tensile specimens that served to execute the experiments. The as-built SLM titanium alloys consist of particular martensite due to the rapid cooling rates obtained during the SLM process, which results in high tensile strength but poor ductility. It was found that increasing the number of melting steps from single to triple melting increased the cooling rate, which refined the microstructure. It resulted in improved mechanical strength but lower ductility, as it can be seen on the lower left picture. Observed on image G, the circular martensite decreased in length but increased in width. At the same time, there was an increase in the number of internal defects, which gave small contributions to the mechanical strength. Also, we can see SEM images of single melting, A and B, double melting, C and D, and triple melting, E and F samples. In rapid solidification process, as in the SLM process, when not enough time is given for the heat distribution, pores are formed due to the lack of fusion. There are two categories, one being the lack of fusion pores, which have an irregular shape and are dependent on the SLM process parameters. The other category is a metallurgical pore with a spherical shape, which forms due to the presence of absorbed or entrapped gases. Increasing the melting steps vanished the fusion pores and the spherical pores were reduced in number and size, as observed on the lower right image. The lower left picture shows a hardness map of the three layers laser melting process respectively. It is seen that a homogeneous distribution of hardness is achieved on the triple melting process due to the reduced pores. The authors suggest the use of remelting the layer process, stating that the increase in mechanical strength and homogenization of the samples can compensate for the cost and time increase.